Hey everybody, Chris McClure here. Now we're going to move on to section R.2, continuing on our journey to review everything that we should have learned before actually starting the class, but hey, it's a review, so it's all good. So now we're going to be talking about some specific things with real numbers, now that we know what real numbers are. So let's take a look at the real number line. Real number line is nothing more than just a horizontal line. And notice, by the way, that the arrowhead is on the right-hand side, goes to the right. So that indicates that as you go from left to right, you are increasing in value. Now, you could scale your number line any way that you want, but, this is a pretty common depiction, just enough to where you can, have tick marks for every integer, but also there's enough room for you to show you locations of some non-integer numbers like negative 1/2, positive 1/2, square root of 2, which is about 1.4114, something like that. 1.414, I think. Anyway, so if it's 1.4, say, then that should be 4/10 the distance between 1 and 2. Here you got pi. Remember, pi is 3.14159, so it's a little bit beyond the 3 tick mark. Here's negative 1/2. One thing to keep in mind as you go from right to the left of 0, you're actually increasing in magnitude, but the numbers are becoming less and less relative to each other. Negative 3 is less than negative 2. But negative 3 is larger in magnitude compared to negative 2 because it's further away from 0. So the location of a number, we say that that location is a point. We can call that point any letter of the alphabet that you want, but suppose it's P. A number is that point P. We call that the coordinate of P. What's the coordinate of P? Well, it's the number. So, for example, if, your point was here at 2, the coordinate of P would be 2. Okay? So, like I said, the real number line is just nothing more than a straight line, and we associate all the real numbers as being lined up on that line. Goes on forever in both directions. Every real line has to have a 0 somewhere, which we call the origin. Notice the big fat O right there, that means origin. So 0 is at the origin. You go to the right, you have the positive real numbers. Go to the left, you have the negative real numbers. And, we know that when you add two positive numbers, you get a positive number. You know that when you add two negative numbers together, you get a negative number. When you add a negative plus a positive, you may end up with a negative or a positive number, depending on if, the relative magnitude of the two numbers. If the negative number is more negative than the positive number is positive, then the result of adding the negative plus the positive will be negative, and then vice versa. Now we could talk about multiplying two numbers together. If you multiply two positive numbers together, you'll always have a positive number. You multiply two negative numbers together, that result will always be positive. Remember, the negatives cancel. And if you multiply a positive times a negative number, the result is going to be negative. Now, when we talk about graphing inequalities, what we're talking about is, saying on the real number line, we could plot the 2 points and say that the number on the left is going to be less than the number on the right. Say we've got two numbers, A and B. If A is to the left and B is to the right, that corresponds to the statement that A is less than B. If A and B are really the same number, then they'll have the same point. And that corresponds with the statement A equals B. If A is to the right of B on the number line, then we say that A is greater than B, using this notation there. Notice that the little point here points to the smaller number. The smaller the point points to the smaller number. The larger area of the symbol points to the larger number, because guess what? Think about this as a mouth, and this is Pac-Man eating the larger number. So, it is true that 3 is less than 7. That's a true statement. Negative 8 is greater than negative 16. That's also true, because negative 8 is closer to 0 than negative 16. It's true that negative 6 is less than 0, because negative 6 is to the left of 0 on the number line. Negative 8 is less than negative 4. That's true as well. All right, and so forth. 4 is greater than negative 1. That's true, because 4 is to the right of negative 1 on the real number line, and so is 8 is greater than 0. That's positive, or that's a true statement as well. If we say that a number A is greater than 0, like we see here, that's equivalent to saying that A is a positive number. Likewise, when we see that A is less than 0, that's the same thing as saying that A is negative. So I got a question for you. If I were to say some variable x is greater than 4, well, what could x be? Well, x could be a whole range of values. So what values of x will make this a true statement? How about 5? Or 6? Or 10? How about 4.1? Yeah, all of those numbers are greater than 4. In fact, we could plot the graph of this inequality just by placing this little open parenthesis pointing to the right, and then we could shade the real number line going to the right. Now, this tells us that any number to the right of 4 on the real number line will satisfy this inequality, but not including 4, because 4 is not greater than 4. But any number that's to the right of 4 on the real number line, including 4.000000001, will satisfy that inequality. Let's look at part B. We have the inequality x is less than or equal to 5. What could x be? Well, here's how we can graph it. Notice here that we've got this little closed bracket here, pointing to the left at 5. And we shade to the left of 5. So we'll say that any number that's at 5 or to the left will satisfy this inequality. Any questions about inequalities? Now, when we talk about distance between 2 points, all we're doing is plotting the 2 points and counting the number of tick marks between those 2 points. And we say that the distance is so many units. Like, for example, there's 3 units between 0 and 3. Or that there's 4 units between negative 4 and 0. Another way of talking about the distance between a number and 0 is by talking about the absolute value of that number. Here we have the 2 vertical bars around A. That means absolute value of A. And you know what? If you're taking the absolute value of a positive number, the result will be that number. But if you're taking the absolute value of a negative number, then the result will be that negative of that negative number. So, for example, the absolute value of 2 is 2, but the absolute value of negative 2 is positive 2. All right, the absolute value of 8 is 8. Absolute value of 0 is 0. Absolute value of negative 15 is 15. Absolute value operator just strips off the negative and makes it non-negative. either positive or 0 in the case of 0. But if we want to calculate the distance between a number and some other number, then we could use this sort of notation. Suppose that we've got a number at point P and another at point Q. So suppose that A is at P and B is at Q. Then we want to talk about the distance between P and Q. We can use this sort of notation here. And that's going to be the absolute value of the distance between them. So it really doesn't matter if you want to do B minus A or A minus B. You're just going to take the absolute value of the difference of the coordinates. Okay, so that's why the distance between P and Q is the same thing as distance between Q and P. So suppose that point P has coordinate -5, point Q has coordinate 7, and point R has coordinate -3. Suppose we want to find the distance between point P and point Q. All we need to do is take the difference between -5 and 7. So we could do 7 minus -5 or -5 minus 7, either way. Here's P, here's Q. And if you count, the number of units between P and Q, you can just simply subtract the coordinates, 7 minus -5, which is 12. You could also do -5 minus 7, which is -12. Absolute value of -12 is 12. Either way, you still get the distance of 12. If you had to answer the question, what's the distance between Q and R? Well, Q has coordinate 7, R is at -3. So you have -3 minus 7 is, -10. Absolute value of -10 is 10. So you could say that the numbers 7 and -3 are 10 units apart. This distance should never be negative. It's either going to be positive or 0 if the numbers are the same. Okay, moving along here. Now, when we talk about evaluating algebraic expressions, what we talk about is finding the value of the expression. That's what we mean. Find the value of the expression when your variable or variables are specific numbers, specific values. So suppose that we have the expression x plus 3y. All right, so the value of this expression can be anything, but it really depends on what x and what y are. Suppose that in this problem, x is equal to 3 and y equals -1. Then the value of x plus 3y will be, well, we'll plug in 3 for x, and we'll plug in -1 for y. Then we'll have 3 plus 3 times -1. And we know from the previous discussion that you will multiply 3 times -1 first to get -3, and now you'll have 3 plus -3 is 0. So the value of x plus 3y is equal to 0 when x is 3 and y equals -1. So this is what we mean by evaluating the expression for these specific values of the variables. 5xy, so again plug in 3 for x and -1 for y, and you end up with -15. Here we've got 3y over 2 minus 2x. Again, plug in -1 for y and 3 for x. And you simplify, and you end up with 3/4. Moving down here to part D, again plugging in 3 for x and -1 for y. As you can see here, we end up with 13. Making sure that you understand that the absolute value bars act as a grouping symbol. So you're going to figure out what's the value of the stuff in the within the bars. In this case, you end up with negative 13. And finally, your last step is to take the absolute value of negative 13 to get 13. All right, moving along here. Now, when we talk about the domain of a variable, what we mean is, asking ourselves what range of values can we plug in for the variable or the variables if it's a multivariable. But we'll typically deal with just a single variable sort of expression here when we talk about finding the domain of a variable sort of expression. So suppose that we've got 5 over x minus 2. Well, what could we let x? X could be actually anything. Except 2, because if x were 2, then the denominator would be 0, because 2 minus 2 is 0. So we would have to exclude 2. We know that we cannot divide by 0. That's why we are excluding 2. But any other real number can be plugged in for x. Like 3 or 10 or 17 or negative 2 or whatever. You can plug in for x and simplify and you get a real number. So here's what we can use to talk about the domain of this variable expression. We just simply say x could be any number except x cannot be equal to 2. That's really what this set means. So this is the domain. So we're talking about using these relations where we have an equation where you have one expression being set equal to some other expression. Well, one expression could just simply be one variable, and the other expression could be some sort of formula. So as in, for this example, the circumference is equal to 2 times pi times the radius of a circle. That's how we talk about finding the circumference of a circle. Circumference is nothing more than the perimeter of a circle. So r could be anything. Typically, though, r is going to be a positive number. Doesn't really make sense to have a negative radius, huh? So we could talk about the domain being greater than 0. If you think about C being dependent on R, well, R could be any positive number. If you want to talk about the set of possible values for C, well, it will also be positive, because it doesn't make sense to have a negative circumference or a 0 circumference. All right. Now, again, remember, we're not spending much time on any one topic. If there's any of these that you need extra material on, let me know, and I can point you toward an intermediate algebra textbook or something. So anyway, moving right along, laws of exponents. We will review exponents. When we take a number raised to a power, what we're really talking about is repeated multiplication. When a is some number, n is some power, which means n is going to be some positive integer. Doesn't have to be a positive integer, as we shall see. But suppose that n is a positive integer. A to the nth power means a times a times a times dot dot dot, where you have a written down n number of times, and there you have n factors of a. So it's just shorthand for repeated multiplication of a number with itself. By the way, a raised to the 1 power is always as a itself. Any number raised to the 1 power is itself. Any number raised to the 0 power is 1, provided that the number itself, a, is not 0. We don't know what 0 raised to the 0 power is. We could define it for the purposes of a specific discussion, But generally speaking, though, 0 raised to the 0 power is undefined. But that base of exponentiation has to be any other number besides 0. Now, with the negative exponent, like you see here, that means take the reciprocal of a and apply the power. A to the negative n power means 1 over a to the n. Means that you take the reciprocal of a and apply the nth power. So, for example, if you had 2 to the negative 3 power, well, that means 1/2 raised to the third power, which is 1/8. If you have x to the negative 4th power, that means 1 over x raised to the 4th power. And if you have 1/5 raised to the negative 2 power, well, the reciprocal of 1/5 is 5. So that means 5 squared, which is 25. Here's the laundry list of laws of exponents here. I'll let you look at these. I think you've seen all of these before from a previous math class. Take a look at some examples here. Suppose that we have x to the negative 3 times x to the 5th. Because both of these exponential expressions have the same base, then all you need to do is add the exponents. So negative 3 plus 5 is 2. So you have x squared. So this first example uses this first law of exponents. Now let's move on to part B, using this law right here that tells you to just multiply those exponents. And by the way, x to the negative 6 is 1 over x to the 6th. And this third example here is going to illustrate this law right here. So you're going to have 2 cubed times x cubed. But 2 cubed is 8. So we're talking about 8 times x cubed. This last example right here corresponds to this law right here. So we will just subtract the exponents. Negative 2 minus negative 5 is positive 3. Oh, sorry about that. I skipped this one here. But focusing on this one right here, just subtract the exponents. You have x cubed. This one right here is using this law right here. So 2/3 raised to the 4th power means 2 to the 4th over 3 to the 4th. Okay. Square roots. Now when we talk about the square root of a number, we're talking about that positive number whose square is equal to the number that you're taking the square root of. Here are some rules regarding square roots. As long as we're staying in the real number system, then you can't take the square root of a negative number. Square root of 0 is 0, at least that's the principal square root. And by the way, when you see the symbol, the square root symbol, we mean the principal square root. The non-negative real number is the number that you're taking the principal square root of. And the result is going to be that positive number whose square is equal to a. So the principal square root of a positive number is positive. Now, if you are taking the square root of a non-negative number and then you square that result, you should always get that same number back. So if you're taking the square root of 2 and squaring that result, you should always get 2. And square root of 3 squared is 3. Square root of 10 squared is 10. Square root of 64 is going to be 8 because 8 squared is 64. Well, negative 8 squared is 64, but What we want is the positive, or at least the non-negative number whose square is equal to 64. And that result is 8 in this case. B, square root of 1/16 is going to be 1/4 because 1/4 squared is equal to 1/16. Square root of 1.4 squared is equal to 1.4 because the squaring operation and the square root operation are inverse operations of each other. And the square root of 2.3 squared, the square root of 2.3 squared is going to be 2.3. But when you're taking the square root of the square of a number, you're essentially taking the absolute value of that number. Remember, the result of taking the square root of a number is always going to be some non-negative value, meaning it's either positive or 0 in the case of taking the square root of 0. Square root of then of negative 2.3 squared is going to be 2.3. It's the absolute value of negative 2.3. So this actually kind of gives you a slick way of rewriting the absolute value operation. You could say the absolute value of a is equal to square root of a squared. Square root of x squared then is square root of x. Alright, if you want to use a calculator to evaluate exponents, that's no problem. Hey, I brought my calculator with me. Hey, there's my calculator. If you want to do 2.3 raised to the 5th power, well, this is how you do it. And by the way, on these newer versions of the TI-84 Plus, when you do the exponent, you have to hit the right arrow to get out of the exponent mode. Then execute. So that's how you do exponents on your calculator. If you need to do negative exponents, no problem. 2.3 raised to the negative 2 power, for example. There you go. When you want to raise it to a negative exponent, use this symbol right here, not the minus operation. Use the negative operation. Okay? Alright. Scientific notation is just a shorthand way of expressing extremely small numbers or large numbers that have a lot of digits or decimal places. Here's the general recipe, the rules of the road for talking about converting a decimal number to scientific notation. So basically what you have to do is you have to count the number of places the decimal point must be moved to arrive at a number x where x is between 1 and 10. Less than 10, greater than or equal to 1. Now, if the number that you're trying to write in scientific notation is larger than 1, then your number will look like this in terms of scientific notation. You'll have some number times 10 raised to some power, positive power. But if the number that you're writing in scientific notation is smaller than 1, then you're going to have a negative exponent on the 10. So, for example, 9,582 written in scientific notation. Well, here's how we do it. You would just put the decimal point at the end after the last digit, and then you count the number of places that you move your decimal place so that you end up with your digit on the left in the ones position. So you had to move it 3 places to the left. That means that you have an exponent of 3 on the 10. And this number right here is between 1 and 10, so it follows the rules. 1.245, there's really nothing to do with this except you'll just have a times 10 to the 0 power. Why do we not have to do anything? Well, because 1.245 is already between 1 and 10. So you can write it like this in scientific notation if you want. Now regarding 0.285, well, you'll have to move the decimal place the decimal point 1 unit to the right. So 2.85 now is a number between 1 and 10. And because of the fact that we moved the decimal point 1 place to the right, we have a -1 exponent. When you have a negative exponent for your number written in scientific notation, that means that the number is smaller than 1. And for 0.000561, move your decimal point 4 units to the right, so that now you have a non-zero number and just 1 digit to the left of the point. And so now you have 5.61 times 10 to the -4 power. This -4 corresponds to the 4 places we needed to move the decimal point to the right. We can go in the opposite direction. If we need to go from scientific notation to the decimal, then we could just reverse the process. If you want to take 2.1 times 10 to the 4th power written as a decimal, then we'll write our 2.1 and then count 4 decimal places to the right to end up with 21,000. 3.26 times 10 to the -10th power. Well, guess what? We're going to move 5 places to the left for our decimal point to arrive at 0.0000326. Why? Because there's 5 places between the decimal point there and there. 1 times 10 to the -2 power. Well, here's your 1.0 and move your decimal point 2 places to the left. So you have 0.01. So if you see that the smallest living cell is only about 0.00001 centimeters, well, that's pretty clumsy to write. It's going to be more compact in scientific notation. You can write it like this: 1 times 10 to the -5 power. Why? Because there's 5 decimal places that you have to move to get your number written properly in scientific notation, so that this number right here is some number between 1 and 10. And if you were given this number right here, that the whole surface area of the Earth is about 1.97 times 10 to the 8 square miles, then, you just take that decimal point right here and then count 8 units to the right. And you end up with 197 million square miles. Now, on your calculator, if you want to use scientific notation, then you'll use this button right here where it says EE. So if you wanted to do 7.56 times 10 raised to the, well, then we'll use that symbol right there, to the 12th power or something. And that means 7.56 times 10 to the 12th power. Or if you want to do 7.56 times 10 raised to the -12th power, then we can use that. Okay? That's how you do it. Now, if you are doing operations with numbers written in scientific notation, then you need to make sure that you use parentheses. So if you wanted to take this number 7.56 times 10 to the negative 12th power times some other number, then just put the whole thing in parentheses. And then times, let's multiply it by some other number in scientific notation. 1.23 times 10 to the, say, negative 11th power. Enter. There you go. Alright, so that's it for section R.2. I'll be back with another video tomorrow for section R.3. Again, let me remind you about proctoring form. If you have not yet decided on a place to take your test, if you are outside of a 50-mile radius of any DMAT campus, then you need to really be working on that as soon as possible. I'll email out the proctoring form again for those people who might have overseen it or overlooked it. And I'll also post that proctoring form on Blackboard as well. So look for an appropriate place to get your proctoring done and get that form filled out and sent to me, okay? Well, I'll cut it off here, and I'll talk with you tomorrow, okay? Take care, folks, and have a good day.